right, so it's time to do some practice problems with conservation of energy. And I've got a couple different examples here, some with friction, some without. These are actually from the spare problems that you have at the end of the unit. The answers are there, but I thought I would go through some of the explanation of how they work. So this one, we're looking at a pendulum, really, and we haven't done a whole lot with pendulums, but let's just draw ourselves a picture here and see what we can come up with. So let's say that's the monkey, because of course that looks like a monkey, right? And we have a 25-meter long vine, and let's see, initially he makes an angle of 28 degrees to the vertical. Now this is going to be a little extreme, but you'll get the idea. All right, so let's say 28 degrees right there. How fast will the monkey be traveling when she travels to the bottom of the swing? Okay, so this is where I start, and this is where I end. The reason that pendulum problems are kind of classic is because when you do the LOL, hopefully it is easy to see what the heck's going on here. So we have the monkey, of course, right? We have the earth. So when the monkey is here, where you start, right? If we assume that this is our height of 0, then we have some height off the ground here. Okay, so we're looking at potential energy. All right, and that's really the only one we have, and for the sake of room, I'm just going to leave the other ones out. When we're down here at the end, we are going with a maximum speed. That is the fastest, right? If you've ever ridden on a swing in the playground, you know that what's going to happen is that when you're at the bottom of the swing, you are going the fastest, and of course you slow down on the way up. All right, so this is the gist of our LOL, and we need to figure out how fast we will be traveling at the bottom of the swing. So we can very quickly set these two equal to each other. And here are our formulas. And look, the mass cancels out, so honestly it doesn't matter. So GH equals 1/2 V squared. Multiply both sides by 2. And so V is going to be the square root of 2GH. Okay, so G is easy, but what about height? How do we figure out that height? And that is where our lovely little triangle and some trig comes into play. So let's realize, all right, obviously that's where our H is. So if I say this is 25 meters, right? We really want to know the distance from here to here, and it's not 25 meters when it's like that, right? It's some other length, right? So I don't know, let's just call it length L, right? But it's definitely shorter than the 25, because the 25 takes us all the way down to here, and that's not where we are. Okay, so if I'm looking at trig, of course this is my hypotenuse, this is my adjacent side, so cosine of 28 equals the adjacent side, which is L over the hypotenuse. So if we say 25 times the cosine of 28, this will give us, I might be having a little bit of a flashback, right? Let's see, 20, whoops. Sorry, I'm working a calculator as I talk to you guys. So that means that L is 22.07 meters. So if this is 22.07 meters, that means that the height here is going to be 25 minus 22.07. It's the difference between the two. Correct? Correct. So that means that the height is equal to 2.93 meters. All right, give or take a little with rounding. So if I go to figure this part out, 9.81 meters per second, and our height of 2.93 meters. So then we can, let's see, let's just type this in. If I'd have been smart, I'd have worked them all out before I got on the recorder, but I didn't do it. All right, so I get a velocity of 7.58 meters per second, assuming I did not make a math mistake. So that's how you would solve a problem along those lines. Now notice what we don't have. We don't have work, we don't have friction. The only tricky part to this is the pendulum and figuring out the height, but otherwise this is a very standard energy conservation problem. All right, so let's take a look at our next one. Inclined plane, and we've got some friction, So there's a whole bunch of stuff here. All right, what is the potential energy of the block before it begins to slide? What is the work done by the friction and speed of the block when it reaches the bottom? Okay, let's do a quick LOL for this one. All right, so we've got the block, right? We've got the Earth, because we've got potential energy, of course. And we are going to lose energy, thank you very much, to friction. I'm going to write it this way to start with. All right, so this is my start position. And this is my end position down here when it reaches the bottom. So what I would consider is at the start position, it is at rest. So it's got potential gravitational energy. And when it's at the bottom, it has kinetic energy, no springs, and so on. So if I write this as an equation, my potential energy will be equal to the work done by the friction plus the kinetic energy. Now that's one way to do the LOL. You could also consider it to be thermal energy. However, I'm just going to actually write that over here. The work done by friction can also be the same as the E therm, right? But I don't need to do it twice. I don't need to redo it. And you know how I know to just work with friction or to do work instead of E therm is the question itself asking me for the work done by friction. So I might as well consider that I'm doing that I'm going to look at this from a work perspective versus an energy perspective. Now, the other thing I want you to notice what I just did there with the blocks. I know I made them the same height, but that was just me being sloppy, right? 3 of them over here, 2 of them over here on the right. That's because work is taking energy out of the system. That is the function of work. Work either adds energy to a system or it takes energy away from a system. All right, so with this in mind, this is where I'm going to begin. All right, now we have a lot of calculating to do here because we don't even know the height. So let's start there. All right, but mgh equals force of friction times the distance, that's work, right, plus 1/2 mv squared. That's where I'm going to eventually go, but I don't know this, I don't know this. Luckily, I know the mass. Coefficient kinetic friction is in there for some reason. Oh, that's going to help me find the force of friction. Oof, we've got a bunch. All right, so let's start at the beginning. Let's start with figuring out the height. Let me change colors too. So if we go to figure out the height, if I know that the hypotenuse is 5 and my angle is 36, right, this is the opposite side. So sine 36 equals the height over 5. So 5 sine 36 equals the height. Make sure you're in degrees, not radians. And so 5 sine 36 is 2.94 meters. Okay. I'm going to write it over here because I'm going to need that a little bit later. All right, so I got this one taken care of. Now let's figure out friction. Sometimes I'm trying to find friction if I know all this other stuff, but as you know, I'm trying to figure out the velocity of the block, so that's not quite the same thing. I'm going to have to use the coefficient of friction formula to help me out here. So mu equals force of friction over force normal, blast from the past, right? So I want to do mu Fn equals force of friction. Now, I know mu, but what about Fn? Well, it's been a while since we've done this. I'm going to rewrite the block right there. mg, right? This is our triangle within the triangle type of problem, and our normal force is not the same as mg in this case. It's actually the same as this side, which is the cosine piece of the triangle, and that angle is still 36 degrees. So if you don't remember that at all, go back into unbalanced forces and balanced forces. There's a ton of stuff with inclined planes in there, and you can take a look and refresh your memory. But that's why this is kind of an extra problem versus anything else. So 0.22 is my coefficient of friction. The mass is 25, 9.81 for the gravity, cosine of 36 degrees. Again, make sure you are in degrees, not radians. So 0.22 times 25 times 1 times cosine of 36. Force of friction is 43.7 newtons. Okay, so now I've got this one over here. The distance that that's going to travel is 5. Now I think I have enough information to actually set it up and solve for everything. So let me change colors one more time and see what we can figure out. Okay. All right, so we'll throw some answers into here pretty quickly. 25 kilograms, 9.81 meters per second squared, and our height is 2.94 meters. That's the left side of our equation. I'm going to just type that in quickly to get the answer to A, which is what is the potential energy, and I get 721.04 joules. All right, so there's your answer to A. Equals. The second part was the work done by the friction. The work done by the friction is going to be the force of friction times the distance. So 43. Whoops, actually, let's do this. Let's try to carefully move that out of the way. All right. So I'm going to do 43.7 newtons times the distance of 5 meters. Which is 218.5 joules. So there's the answer to B. What is the work done by friction? All right, plus 1/2 25 V squared. Okay, so half times 25 is 12.5 V squared. Right now I should be good to go. Remember, you're adding that together, so you're going to subtract on this side. So 721.03 minus 218.5 gives me 502.5-ish joules equals 12.5 V squared. Divide both sides by 12.5. Let's see if we can do this without running out of room. V squared, and so V will equal the square root of that. And you get 6.34. All right, that is about as difficult as a problem can get. I mean, my goodness, coefficient of friction, I do not believe I would be asking you something like that on a test, but you should be able to do it. All right, but something key that you should realize is that I could also identify this as E therm, right? If I give you the value or say how much energy was lost to friction, if I give you the velocity value, you should be able to do that. All right, so there's that one. Here's our last one. Now, power is something we haven't really talked about too much yet, but it's worth bringing up, assuming that you're going to get those notes very, very soon. Okay, so a little bit about power. This is actually a pretty straightforward question, but it would help to know a little bit about what power is. Power is the rate. How fast can you do work? So a straight definition is to say, well, it's how much work I can do in the amount of time it takes me to do it. You can expand this, though, into a couple of other possible definitions. We know that work is force times distance, so I could say it's the force times the distance over the time. Now, in this particular question, if you look at this question, you say the bear with the man, blah, 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 runs up a hill. Okay, so here's the bear, right? Bear runs up. All right, that doesn't look like a bear to begin with, but now it looks like the bear grew something out of its head. That's really not so smart. All right, so here's the bear again. And if you think about it, what did the bear do? The bear went up a height and it gained potential energy, right? Gained some gravitational potential energy. And if you think about the formula for that, that is the same as the force of gravity. This is the same as distance. So a third possibility when we are lifting something is to say mgh over time. That's if you're just changing potential energy, though. So be careful. It's this type of a situation. And if you think about it, it makes sense, right? The bear is lifting herself against gravity. So that's the force, right? We're just defining it a little more closely. If we're going to work with this definition in this particular problem, Another thing I want you to keep in mind, it introduces the kilojoule. Kilojoules or joules are very tiny. Kilojoules are just like kilometers, right? You have 1,000 joules in 1 kilojoule. So what this is 23,500 joules. It's a bunch. Okay, just move that decimal over 3 times, multiply by 1,000. So if I'm going to figure out how high the hill is, let's work with the whole thing here. Power equals mgh over t. Because we're lifting, we want to isolate h. I'm going to multiply both sides by t. pt equals mgh. And then I'm going to divide by mg, and then it'll give me h. So, rats. I just realized I misread this whole problem. There's no power in here. We were just doing work. Oy, oy, oy. Skip the time part. All right, wait. We'll do this. How high was the hill? I'm going to change the question. If she goes up in, I don't know, 5 seconds, I'll just add. That way I can make the problem the way it's supposed to be. I'm sorry about that, guys. All right, so you're probably sitting there going, what's she going to do about the fact that there's no time in here? I'll just add the time. I'll just make it up. Because that's what I get to do. I'm in charge, right? That's no big deal. All right, so here's the mass and then 9.81. All right, so now I'm going to figure out the height of that hill. Let's hope it's not something too crazy since I made up the number, right? That would be kind of ridiculous. Let's see, divided by 218 times 9.81. Well, it's a little tall. It's a little tall to expect anything to run up this kind of a height, but whatever. We're just going to pretend it's like the most powerful bear ever. Maybe it's Sasquatch. Who knows? Who knows? But you get the idea. Okay. So it's worth noting that, these notes on power, in case power is something that is eluding you a little bit or you're getting to that spot in MOPS and we haven't necessarily covered it yet. But there are some extra practice problems there. And yeah, another thing you could also consider, right, if I was going to make you do an LOL diagram for this, I'm trying to think of what else we could do here, right? But LOL, what I would say down here is I've got kinetic energy, UG, US. I mean, obviously there's no spring, there's no potential because I'm on the ground. And I would say I start from rest, right? So the O would have work going into it, right? And then my final L would be all UG. So that would be another example of energy being added to a system as something going up the hill. All right. Hopefully you found these a little bit helpful. And there's plenty more at the end of the unit if you need them. All right now.